So students usually understand continuity graphically a lot better. Let's do that first, and then I'll show you the calculus definition of a continuous point. So this is an example of a continuous function, and the reason is because you can follow this curve with your finger, and you never have to lift your finger. You can put your finger right on this curve and trace it the entire way. So this function is discontinuous at a point. Right here, there's a hole, and we have to jump up here. We call that a removable discontinuity because you have to lift up your finger and then put it back on this dot. So that's called a removable discontinuity. We have infinite discontinuities, which would be like a vertical asymptote. That's a pretty bad vertical asymptote. Should have made it more vertical, but you get the idea. This is an infinite discontinuity because you can continue tracing with your finger, but it's for an infinite amount of time. It never stops climbing. And one last one. No, I think there's two more. Jump discontinuity. So if you got a function that's working like this, and there's an open hole, and then there's a dot down here, that's removable right now. It definitely looks removable. But then if I make a curve here, we call that a jump discontinuity because all of a sudden we jump from one type of function's behavior to another. So you see that a lot with piecewise functions. And then the last one is an oscillating discontinuity. So you see this with trigonometric functions a lot. So if you had a function that looks like this, or it gets more and more wavy the closer you get to the origin, that has an infinite discontinuity, not an infinite, sorry, an oscillating discontinuity at x equals 0. We never approach a point because the closer you get to x equals 0, the faster and faster the thing moves up and down. Okay, so with all those in mind, all the points of continuity and discontinuity. Basically, you want to focus on the points of discontinuity. And everything that's not a point of discontinuity on the domain is a point of continuity. So a divide by 0 is the biggest thing I'm looking out for in this one. If I rewrite this, it's x plus 1 over, this can be factored, right? Two numbers that multiply be 3 but add up to be negative 4. That's x minus 3 and x minus 1. Okay, so these don't cross cancel, right? That's one thing you always want to check for. But we have two infinite discontinuities at x equals 3 and x equals 1, because if you were to plug those in, you have a divide by 0 error. So those are vertical asymptotes. So those are infinite discontinuities. Okay, y equals natural log of x plus 1. Remember, you can never have the natural log of a negative number. So that's one thing we want to look out for. Can't have that. So we want to make sure this is greater than 0 and strictly greater than. It can't be greater than or equal to. Okay, because you can't have a natural log of a 0 number. You can't raise e to a power to make it equal 0. So if I solve, I get x is greater than negative 1. So that's actually the domain of this function. You can only plug in a number greater than negative 1. And so that is all the, I'll go back to the next one. That's all the points of continuity, negative 1 to infinity. There's no jumps. If you study the graph of a natural log, it looks something like this. Okay, so there's no jumps, no removable discontinuities. This is a regular natural log function, just shifted one space to the left. That's what the plus 1 does. So that's it. There's no jump discontinuities in that graph. Okay, so when you first do these, you probably want to plug them in a graphing calculator just to check. And by the way, this one over here, the domain is negative infinity to 1 union 1 to 3 union 3 to infinity. Okay, and just as a refresher in interval notation, you always go least to greatest. What's the smallest number you can plug in for x? Well, we never reach it. Negative infinity. Negative a billion's fine. Negative a trillion's fine. But 1 isn't fine. That's why I use the parentheses, because a parentheses means you can't have exactly 1. And then a union and a parentheses. So everything up to 1, and then everything a little bit bigger than 1, but a little bit less than 3. We got to jump over those discontinuities. So that's points of continuity. This one had no discontinuous points. Excuse me, sorry. This one's a fun one because absolute value of x over x, it's almost like it's x over x, which it's always going to make 1, you would think, right? But think about the negative numbers. If you plug in a negative up here and a negative down here, then you're going to have a positive divide by a negative. So every negative number on this graph is going to be negative 1. Because if you plug in negative a billion in for x, then you're going to have a billion divided by negative a billion. It makes negative 1. And then once you get to this point, x equals negative 1, Then you jump to x equals positive 1, because if you plug in a positive billion and a positive billion, then you're going to get 1. Doesn't matter what you plug in. 10 over 10, that also makes 1. So this has a jump discontinuity, jump at x equals 0. And it's continuous everywhere else. So continuous everywhere else.